Put on. I showed you welding electrodes before. This is the biggest electrode, okay? They actually have machines, and they use about 2,000 amps, and they basically repair big iron castings. So here's a guide for welding iron castings, and here's an ingot mold, and some guys using a gas metal arc torch, but they also use these if anybody wants to. Anyway, you want me to pass it around? It's just a big hunk of steel with slag on it. But anyway, here it is. The other thing, oops, well, I won't pass it around. It's going to roll all over. Another thing I will pass around, since Mike talked about standard welding symbols. Here's the AWS manual on standard welding symbols, and you will find them on CAD programs that when it gets to welding, they'll show you how to weld things. We don't need to go through those things. This is the structural welding code, this thick, okay, for plate for bridges and buildings, I-beams. This is the structural welding code for sheet steel. You can tell this is plate thickness and this is sheet thickness. Okay, I mean, it's just why is sheet metal welding not a big code? Well, who does the most sheet metal welding? People like General Electric, Appliance Park, where they're making refrigerators and washers, and the automotive companies. They write their own specifications. They don't need some national professional society. Whereas all those bridge builders and architects and smaller firms that are building, could be billion-dollar firms, they need kind of a national code. So the sheet metal welding code's not a very significant code, okay? And that's because each company basically develops their own specifications and procedures, so far as that goes. The American Welding Society and a lot of other code writers, I actually have a module on codes and standards. American Welding Society knows they could make a lot of money by selling codes, and so they have part of the structural welding code, the D14 series. The big structural welding code we've been talking about is D1 for steel, and D2 or D1.2. D1.1 is steel, D1.2 is aluminum. We'll talk about that later. D14 are specific industries, welded joints and machinery and equipment, welding of presses and press components. When I talked about that great big 7,500 ton forging press, here's the code that applies to that. It's not very thick. That's partly because it calls out the ASME boiler and pressure vessel code, which is this thick, okay? Welding really heavy steel. The structural welding code goes up to about 1.5 to 2 inches for bridges and buildings and stuff. Presses, heavy machinery and equipment can go 4 inches, 8 inches, 12 inches, 16 inches, and that's where you get into the boiler and pressure vessel code. It's got things for heavy sections. The boiler and pressure vessel code is not just steel, it's all materials. Anything composites, I mean, it's got rules for, that's why it's so thick, rules for all kinds of materials. Any questions about that? If you want to know more about codes and standards, I have a whole 12 lectures on codes and standards. But let me talk a little bit about the structural welding code. This is one of the codes that you might say got thinner. So here's the structural welding code out on 1997, AWS D12-97. And here's the structural welding code 2003. And if you compare the two, the structural welding code got thinner. Now, why would a code get thinner and less complicated? Well, because in 2000, the Aluminum Association came out with the Aluminum Design Manual, which is this thick, okay? So it got more complex. So my trend of complexity in codes holds true. The only reason this one used to have has the design rules. This one refers you to this document for the design rules. So the whole chapter of 100 pages in here on design of aluminum structures, welded aluminum structures, has been replaced by this. And there's actually a 2008 or something like that. You remember, Simone? Yeah, I think the last time was 2008. In any case, there are structural welding codes for these various things. I want to start talking about aluminum. Anybody have any questions? Yes. It depends on the organization. ASME, every 3 years, you get a new update. ASME code right now, to buy the full set of like 12, 13 volumes, maybe it's only 11 volumes, is $16,000 last I looked. Okay? And so people would get very upset if they had to buy a new one every year. For a while, the structural welding code, the code writing organizations have decided, many of which are supposed to be not-for-profits, they find they can make big profits on writing codes. So the structural welding code, which used to be updated every few years as they thought it was needed, they decided about 10 years ago to update it every year, because that way the law requires, if you're building a bridge or a building, most jurisdictions, states or cities in the United States will require this code in the law, which means if you're a designer, this is part of your overhead. You got to pay $400 for this every year. Well, I think a few people screamed, and so now they update this every 2 years. Okay? So it's a balancing act of how much can the professional societies get away with in bringing out new codes. The boiler and pressure vessel code, when you pay $16,000, you get semi-annual updates, and they can be that thick for each volume. They can be thicker than the volume. But what do you get? You get 6 updates in 3 years, plus the original code. And so now this thing is this thick becomes this thick, and every 3 years they condense it back. Okay? And so they have blue, pink, yellow, and you can tell what insert it is, because the contract people sign will say you shall build it to the ASME boiler and pressure vessel code as of March 2014. Well, you better have the current code. You buy a whole set for $16,000 that's good for 3 years. Okay?
How much do these structural codes or codes suggest, we have to pump it out in 2 years on this?
Oh, no. There are a lot of people who spend a lot of volunteer time writing these things. Is it all volunteer time? Some of it's because of their company that they belong to. But if I look in the beginning of this, personnel, this is page after page of people who have contributed to this code. And if you start looking at it and the names and stuff, Dwayne Miller is chair. To become chair of a code like this probably takes 20 years of going to these meetings twice a year. Okay, well, many people are doing this as part of their job. Dwayne Miller started out at, what's the big prefab building guys in Kansas? Butler Buildings. Dwayne started out at Butler Buildings, designing, these prefab steel buildings. Okay, he then went to Lincoln Electric Company in Cleveland, and Lincoln, of course, wants him to, attend these things and put things in the code, or control what's in the code. I mean, whether he's at Butler Buildings designing prefab buildings, steel buildings, or whether he's at Lincoln Electric, the company has an interest in his participating. Who's the vice chair? Sindel, I don't know Sindel. Neumann, I don't know. Morales is the secretary. That's just an American Welding Society person. And you see, here's another guy from Lincoln Electric. Lincoln Electric has enough to do with, they're the world's largest welding company. They put multiple people on there so that when Dwayne Miller retires, they got another guy coming up to be one of the leaders, okay? And when Dwayne Miller can't attend one of the meetings, they'll have someone. Walt Disney World, they build things all the time. Why is this guy? I don't know why Walt Disney World is paying for this guy to come there. But H.H. Campbell III, I'm sure that's Halleck Campbell's grandson. Halleck Campbell was a Harvard grad, and sometimes I tell some stories about Halleck, who was an interesting guy. But anyway, there's all kinds of people. Shell International Engineering and something. Okay, probably Shell Oil, ConocoPhillips, American, Canadian Welding Bureau. Anyway, there's lots of. You look at the names. There's Dwayne Miller again, because this is a different thing. Hobart's the second largest welding company. U.S. Army Corps of Engineers, Massachusetts Department of Transportation, retired, and then another guy. Waukesha City Technical College probably teaches a welding thing. Federal Highway Administration. Anyway, these people are donating their time to write these codes. And the Professional Society, which is managing the whole process, sells these. They used to sell them for like $80, almost at cost. But about 15 or 20 years ago, they all decided this is a good business. And you should see their balance sheets. Okay? Since the American Welding Society started certifying welders and selling codes, they probably can show to the federal government, to the IRS, that they're doing it at real cost. But real cost is all their overhead. They just built a $40 million building down in Miami Beach, right? Okay, I bought a brick. Okay, they get donations. I think I had to pay $500 for the brick. Anyway. Whatever. So it's a business for the nonprofits, but it is also collecting the historical knowledge, okay, of all the failures that have gone before. And I mean, I do teach a section, a section of this structural material sequence that we do on codes and standards, and how actually the theme of that module is, are codes and standards good or bad? They carry with them all the corporate knowledge of all these previous failures we've had for 100 years, and what are the best practices that we know about today, but they also stifle innovation. You can't go against the code. It's written into law in many cases, and if you want to do something novel or different, you got to go get it approved by the code. That could take 10 years and millions of dollars. Okay, so it's on the one hand, and on the other hand, and you know the story about hands, right? Harry Truman once said he wanted a one-armed economist. Okay, so he couldn't say on the one hand and on the other hand. Okay, so I think Harry Truman also said, if you want a friend in Washington, get a dog. Anyway, okay. Any other questions? Yes. What they will do is, in the code, they will have little lines in the margin, typically, of what changed. So, just like you might take a yellow highlighter and put a little line marker on that paragraph in the margin, they will put little black lines. I see if I can find one in here. Maybe they quit doing it in this code. But it doesn't change. Nowadays, it doesn't change that much. Coming up with the aluminum design manual, that was a pretty major change, okay? And that occurs like every 30 years or 40 years. But the other changes are 5%, 10%, so far as that goes. Pardon me? Oh, you can get it online for a fee. You can buy the boiler and pressure vessel code, I think $13,000 for an online version. What a discount, right? You can also get it at the MIT libraries, because they have to pay the $16,000 every 3 years. What do you think part of your tuition's going for? Okay. There's a place in Colorado that virtually will sell online, so you can download in the next 5 minutes, if you have a credit card, okay, virtually any code in the United States. Okay, they are sort of a clearinghouse for codes. That's all they do, is maintain a web server, and you give them your credit. You find the code, you order it online, you give them your credit card for $100,000 or $1,000 or whatever. I've had to buy codes that cost $1,000 that are less than 100 pages. $10 a page is pretty pricey, particularly when some of the pages are just a list of the people who participated. Hey, save me. Oh, I don't need that page. Okay. But this, it's become a racket, and I actually spoke out at a meeting at NIST once and said that the National Institute of Standards and Technology used to be the National Bureau of Standards. And I said, you guys should do something about this. They're basically stifling manufacturing or construction or whatever you want to call it in this country because the overhead, the cost of codes is just going berserk. Go talk to the MIT libraries. They've been, not just the codes, but the journals and everything else. It used to be journals were almost available for the cost of printing. Not anymore. You know, some journals can cost you $30,000 a year to subscribe to a very popular journal. Okay, so anyway, it's a racket. Okay, so, and that fell on deaf ears down in Washington. Okay, that's one of the reasons they don't call me back to meetings, which is a plus. I want you to know. I mean, open your mouth and say things that are not pleasant, and people won't invite you back. Try it sometime. Anyway, okay, this is just looking at a number of materials: steels, titanium, aluminum, magnesium, and you can see that steels have tremendous strength compared to other materials, but if you do it as specific strength, you find everything becomes fairly uniform. In fact, titanium has some of the highest specific strength of any structural alloy system. Magnesium is right up there. Problem with magnesium, it stress corrosion cracks, it corrodes. Anyway, it's the material of the future, has been for the last 50 years and probably will be for the next 50. The aluminum alloys that we're going to talk about now go from the 1000 series. 1060 is electrical conductor. So if you see a high tension line, you know, carrying 300,000 volts of electricity across the landscape, the wire hanging down is made out of 1060 aluminum, and it might be in a work hardened condition like an H18 temper or a zero annealed condition. But in fact, it's not just that. It actually typically is on a steel core because the aluminum is so soft. That aluminum has no strength. And when everybody's got their air conditioners running during the summer, one of the big problems with those big transmission lines is they sag. They elongate, so you got some big tower and another big tower, and in the winter, the catenary looks like that. In the summer, with all the electricity going through it, it looks like that as it expands and the catenary drops. And it gets hot, and aluminum doesn't have much strength when it gets very hot, we're going to find, because it melts at a much lower temperature. And if you have a problem, if you have a little tree here, okay, it will short out. And it doesn't take too much to short out when you got 300,000 volts. Okay, and there have been some major outages, particularly in California, where the catenary came down, hit a tree, and shorted out, and you've now lost your 300,000 volt transmission line, which is quite a few homes. Okay, so people don't have their air conditioning. Worse, if you're having a drought in the area, some of the Southern California wildfires and stuff started by striking the ground or striking a tree, arcing. You got a drought, you're hitting a tree that, you know, a fir tree that hasn't had any water. It's a pretty interesting fireball. Okay, starts a big forest fire. Some of the utilities in California have paid hundreds of millions of dollars in damages for starting these major fires that you read about in the paper, because they've got 1,000 firefighters fighting for 3 or 4 weeks, and homes are being destroyed and everything. Well, there have been some big settlements. And why do the utilities do this? Well, the utilities do it because they're going to get sued, and when they go in front of a jury, they're going to lose, and they're going to lose even more. So they settle for hundreds of millions of dollars, but it's okay. They just put it right back into the rate base, so everybody in California is going to be paying for that. So all these people, obviously, if you lost your home, you want to get your money back, but most of the people don't realize that's why California has some of the highest rates. Okay, they got attorneys. Of course, you've heard the joke, right? How's the joke go? Why does California have so many attorneys and New Jersey has so many toxic waste dumps? Does New Jersey got first choice? someone's frowning out here like their father was an attorney, anyway, or their mother. In any case, we have all these different materials, and it turns out in specific strength, they are all fairly comparable, and it turns out aluminum is one of the best for lightweight materials. Now, the aluminum alloys fall in a number of different systems, and here are some of the alloy systems designation by the Aluminum Association in the United States. The wrought alloys are 1000 series, so the 1060 is 99.5%, or actually, the 1060 alloy is 99.6% aluminum. The 1100 aluminum is 99%. 2000 series is copper-based alloys. Manganese is 3000 series. Silicon is 4000 series, and you can see the different alloying things. 8 is all the others, and so if you've heard of aluminum lithium alloys, they're 8000 series. They don't use the 9000 series yet. They weren't using the 8000 series much when I was a student like yourself, okay? But they have started using them as a catch-all. A lot of the first aerospace, well, I'm going to show you something that the non-heat treatable aluminum alloys, which are the 1000, 3000, 4000, and 5000 series, have lower strengths than the heat treatable ones, which are the 2000, 6000, and 7000. Aluminum copper alloys were the first aerospace alloys, and I think I mentioned that the Wright brothers, the housing for the engine of the Wright brothers aircraft, the first one to fly, was an aluminum copper alloy, and that was sort of new back in 1910 or 1903 or whatever it was. The 6000 series are common high-strength aluminum alloys, general purpose sort of structural architectural alloys, high strength. The 7000 and 8000 series are most of the aviation aircraft, Boeing, Airbus type alloys nowadays. And we'll talk about some of that. Okay? The aluminum alloys, actually I can probably show you. Well, let me back up and go below here. There are casting alloys for aluminum, and it has something similar. The 100 series .0 casting alloys are really relatively pure aluminum, the copper alloys, and then it starts to break down. 3000 series of the wrought alloys was a manganese system, 4000 is silicon, 5000 magnesium, 600 is unused, 7000 or 700 casting is zinc based. So it's not exactly a one-to-one match, but it's reasonably close. And the welding of the heat treatable and non-heat treatable alloys turns out to be quite different, and we're going to talk about that. So here's the 1060 alloy, 99.6% minimum aluminum. 1350 is the 99.5. Those are the big catenaries, the electrical conductors and whatnot. 1100 is garden variety aluminum. 3003, 3004 sheet metal. 3004 is basically Coca-Cola cans or beer cans or whatever. Okay? It's like 30 or 40% of all the aluminum made. And it's got 1% manganese and about 1% magnesium. It's fairly lightly alloyed, but it has high strength, and it's got a lot of mechanical work in it. Work hardening for all you metallurgists out there. And then these are the non-heat treatable alloys. The 5000 series are basically very weldable marine components, naval ships that are made out of aluminum, sailboats that have aluminum. A lot of these things want to be lightweight, and so they use aluminum. But anyway, the 5000 series are readily weldable, and you can get, without very much difficulty, you can usually get 100% joint efficiency. The non-heat treatable alloys have basic temper designations. 0 is annealed, dead soft, if you will. F is as fabricated, right off it comes off the rolling mill in the aluminum in the plant. H1, H2, and H3 are different levels of strain hardening. Strain hardened only, partially annealed, and stabilized, and you have to look up for each alloy what the strength level is. The heat treatable alloys have a T designation that tells you something about their heat treatment. So you can have solution annealed heat treat. I'm going to tell you what that is if you don't know. You can have heat treated, because these are the heat treatable alloys. The W condition is solution heat treated, and it's basically in an unstable condition. It will precipitate naturally at room temperature, and we'll see that. T1 is cooled from an elevated temperature during the shaping operation and then naturally aged. T4 is solution heat treated and naturally aged. So if I'm Werner Ladder Company, I'm extruding the rails for an aluminum ladder that you go buy at Home Depot or Lowe's or something. Turns out I'll extrude it, and I will set up my extrusion press such that the heat from extrusion will heat up that thing. It's going to be hot when it comes out from just the work, and it will be solution treated. It will be heated up so that all the alloying element goes into solution, and then as it cools down, sitting there in the plant as it's cooling down, it will naturally age to the precipitation condition. And so all they have to do is extrude it. The extrusion heat does the solutionizing heat treatment, and it naturally ages as it sits there if you get the right type of alloy composition. Other things might be T3, which is solution treated cold work, naturally aged. There's all kinds of combinations. There's T6, which is solution treated and artificially aged. You put it in a furnace at a certain temperature, and you try to get the maximum strength. T7 is solution treated and overaged. Why would you overage to not get the maximum strength? Because you get like triple the stress corrosion cracking resistance in a T7 that you get in a T6. Okay, if you take some of my other modules, I'll talk about some of those things. So if I look at the weldability of some of these heat-treated alloys, it varies dramatically. A lot of the aluminum copper alloys don't have A grade, they have C grade, which is pretty poor weldability. Essentially, you make an arc weld on one of these things and you have cracks right behind it. Basically, it's not completely it's not completely homogenized, and you'll get aluminum copper eutectic, and you'll get hot tear cracks in solidification, we call it. So you actually form in the heat affected zone, you'll actually melt some of the grain boundaries, if you will, some of the interdendritic spaces, and you'll get liquid. And because aluminum has a 6% volume change on solidification, you get big internal stresses. Residual stresses and distortion are big problems in welding of aluminum. Okay, and you'll get cracking almost every time if you try to weld one of these alloys. One alloy here in the aluminum copper series 2219 has very good weldability. That's what the space shuttle main tank was made out of for many years. Okay, because you had to weld it. You don't like leaks. They found out with Space Shuttle Challenger what happened with leaks of the O-ring. So they used to weld the tank when we had a space shuttle, and they'd use 2219 aluminum. Okay, if you get down to the 6000 series, you get a lot of A and B weldability. 6061 and 6063. The difference, this is typically plate or sheet, and this is typically extrusions. They have A grade weldability. The largest tonnage of aluminum alloys is 6061. Okay, architectural aluminum, door frames, window frames, you name it, you can get good strength in the base plate, but we're going to see you only get about half the strength in the weld because it's heat treated. The 7000 series, some of the 7000 series have very good weldability, some of them like 7075, which was the workhorse aviation alloy from let's say, well, 2024 was the workhorse alloy from 1920 to 1950, and somewhere from 1960 to 1970, 7075 was the workhorse aviation aircraft alloy for things like Boeing and McDonnell Douglas and stuff. Since then, Alcoa has come up with other alloys that have better combinations of properties. But all the aluminum alloys, not all the aluminum alloys, but almost all the aluminum alloys have a phase diagram. So if I'm looking at percent copper or percent magnesium or silicon or zinc, they have essentially a eutectic diagram. This is temperature, that's the percent of whatever the alloying element is. And here's your liquid, here's your solid alpha FCC aluminum, and you'll get some sort of intermetallic precipitate, whether it's a Al2Cu, I don't remember if that's, there's all kinds of intermetallics. I mean, dozens and dozens. Just in the aluminum copper system, there's probably 4 or 5 different intermetallics with different ratios of aluminum to copper. Magnesium has several, and silicon has a bunch. And then you have ternaries, where you have magnesium copper and magnesium silicon ternaries. And so there are, if you want to be an aluminum metallurgist, you get to learn all about intermetallic precipitates that form. But basically for welding, we have 2 regimes. We have kind of a regime right here, and we have a regime over here, where we have a relatively small freezing range. We don't like to work in here where the freezing range is large. Why? Because a big delta T in the mushy zone and a 6% volume shrinkage means lots of strain and lots of cracking. So you like to work with very highly alloyed aluminum, or very relatively pure aluminum, lightly alloyed, or very highly alloyed. You don't like the intermediate stuff in the middle. And so you have to be very careful when you've got an aluminum alloy, even more so than steel in some ways. You got to know what the composition of the aluminum alloy is before you select the filler metal. Okay? If you look at the relative crack sensitivity, that's what we're plotting here, of different aluminum alloys, silicon, copper, magnesium, magnesium 2 silicon, you'll find this is composition of the weld of the alloying element, and all they're doing here is they're just plotting the freezing range or the strain. Okay, it's alpha delta T. Okay, how big is delta T? This is basically delta T for this system. The maximum in here is at 1 or 2%. This is the maximum. Relatively pure. Well, if it's pure aluminum, it melts at 1 temperature, right? If it doesn't have much alloy content, the delta T is small. You get up here towards the eutectic, and you see the crack sensitivity goes way down. So this is a plot of crack sensitivity. Where does it come from? It comes from the freezing range, okay, of the alloy. So you have to be careful, okay? I don't know if I want to teach you that metallurgy right now. If I look at the relative strength of some of these heat-treated alloys, this is 2024, the workhorse heat-treatable aluminum alloy from 1920 to 1950, and still used today. The annealed condition has a strength of 12 ksi. The heat-treated T3 condition, which is optimum strength, is over 50 ksi. T4 is a little like 5 or 10% less, but it has much better stress corrosion cracking resistance. This is yield strength, this is ultimate tensile strength, and here's the elongation. The elongation is about the same in all cases. They have pretty good ductility. Aluminum in general doesn't have the brittleness that steel sees from hydrogen and things like that. Hydrogen creates other problems in aluminum. This is 7075. Again, big increases from 16 ksi annealed, T6 condition, 75 ksi. Not as strong as a baseball bat, an aluminum baseball bat, which could be 100 ksi, but still pretty good. And here's the elongation. We actually, when we start getting these types of elongations, or these types of strengths, we do start losing some elongation in some of these alloys. Here is actually the aluminum copper system, showing you the phase diagram. You have to solutionize up in this region. This is the all alpha solid phase. Here's the liquid, aluminum plus liquid. This is the phase diagram. So you heat up to 550 centigrade or so, and you can solutionize and put all that copper into solution. If you quench it, you can trap all that copper in solution. If you heat it up to intermediate temperatures around 200 degrees centigrade, you can precipitate out and get high strength. You can anneal it in the 300 to 400 degree range. So if I look at the heat treated condition for aluminum, here's the phase diagram for aluminum copper. Solutionize up here, precipitation heat treat here, the time temperature diagram. This is temperature versus composition. This is temperature versus time. Heat it up for 1 hour, 940 F, which is 560 or whatever centigrade. Quench it in cold water, and then heat it up to 340 F, which is like 170 centigrade or something, for 10 hours. Pretty long heat treatment time. These alloys, these heat treated alloys, are fairly expensive. You gotta remember, it takes about, most furnaces, heat treatment furnaces, are about $1,000 an hour. Okay? So whatever you're putting in there, if you're putting in $10,000 worth of aluminum for 10 hours, you're adding, or 10,000, if you're putting in 10 tons of aluminum, you're going to end up adding $1,000 a ton of heat treatment cost because of this low temperature heat treatment and whatnot. Now, what about the heat treatment alloys? What gives them their precipitation hardening? This is the as quenched hardness way down here. It's soft because it doesn't have any precipitates.